Welcome everyone. Thanks for being here so early in the morning for this tutorial. And in a few minutes, I will introduce myself and my colleague Maurizio. But what I would like to point out is that for those of you who are not, let's say, in the field of quantum computing, we are not talking about hypothetical computational models that will be available in the future. But we are talking about computer that you can already use in the cloud. So the one that you see here is a quantum computer. If you have 4 million euros, you can buy a small machine, or you can use in a cloud, even for free. No, not anymore. Till 2,000 euros per hour. And okay, till a few months ago, it was possible to use this machine was available 1 minute per month for free. Okay. We are in the era of quantum computers, but I'm not sure I'm able to use the remote control. Okay, it works. So welcome again. My name is Paolo Cremonesi, and the today tutorial is co-presented by myself and my colleague Maurizio Ferrari da Crema, who is here. And we are from Politecnico di Milano, which is an Italian technical university. For many years, we have been working on recommended systems. So we are within this community. We have been within this community for many years. And then, I don't know, more or less 6 or 7 years ago, for a number of strange reasons, we decided also to start working on quantum computers. And so today, we will try to explain you how these two, technologies can be used together. And I will anticipate some of the questions. So very often we are asked if there are textbooks that can be used to easily and smoothly introduce non-experts to quantum computers. Unfortunately, no. The learning curve, I don't want to scare you, but the learning curve is quite steep. And most of the books that are available are approaching quantum computing from a very, let's say, theoretical point of view, from the very beginning, okay? But if you use LLMs or if you pick up some papers, articles on, you can try to build your own library that is introducing you to the topic. And these are some of our papers that are trying to bridge this gap between quantum computing and information retrieval or recommended systems, and hopefully in a not too complex way. So this is a draft idea of what is going to be the agenda for this morning. So I will start with a more theoretical part on quantum computing. On the general techniques and description of quantum computing, and then we will focus on one specific technology. You will see that there are many different technologies available for quantum computing. We will focus on one technology, and we choose this technology simply because it is the simplest, okay, to start with. And so after the break, more or less, okay, roughly speaking, Maurizio will start being practical, okay, so showing you how to write simple algorithms and how to apply these algorithms to information retrieval and recommended system problems. And our original plan was also to let you use this quantum computer that till a few months ago was available for free, 1 minute, okay? But with 1 minute you can do a lot of things. But unfortunately, the company that is providing this service, they decided to stop the free tier, and as you know, the minimum unit of time that you can buy is 1 hour, 2,000 euros. I think it's a little bit too much. In any case, Maurizio is reminding me that in the past years we have organized a lab in the area of information retrieval, and also with, let's say, information retrieval and recommended systems, where participants to this lab, they have to solve some tasks on RecSys problems, and we will, and within this lab, we give the possibility to the participants to use an online cloud quantum computer. Okay, and this lab will start in few months. And later on in the afternoon, not in the afternoon, after the break, Maurizio will give you more details. Truly speaking, you can use also IBM quantum computers for free, the smaller one. But the IBM quantum computers are the most complex to use, so they're not good for this tutorial. The back button of my remote controller doesn't work, so we can move only forward, not backward, which is good. Let's start with an introduction to quantum computing, and what you will discover, hopefully, is that we're not talking about simply faster computers. So a quantum computer is not a faster computer. It is a computer which is totally different in the way that in the way that it works, because these quantum computers, we will see that they follow the law of quantum mechanics, which are not intuitive for us. Okay, the behavior of quantum computers seems, even if I've been working on this topic for many years, it seems sometimes magical. Okay, and something which is close to science fiction. I want to give you an example. Okay, a toy exercise. Now, suppose we have 4 cards. So we have 3 aces and a joker. Okay. Now I cover the cards, I shuffle them, and then I ask you to tell me where is the joker. Or better, I ask you to write a program that is telling us where is the joker. Okay. So let's start with the traditional computing approach. Okay. And the question I want to ask you here is, with a traditional computer, how many cards do you have to unfold, to turn, before you are sure that you know exactly where the joker is? Okay. So typically, what you have to do, there is one only possible approach. You explore, you turn all the cards one by one. So if you are lucky, oh, come on, it doesn't work, the back button. So, okay. If you are lucky, you turn the first card and the joker is there. Okay, so in the optimal situation, it's enough to, at the first iteration of this loop, you find the joker. If you are unlucky, okay, you have to, how many cards do you have to turn? 3, okay, but okay. Let's assume instead of having 4 cards, you have a huge number of cards, so that n or n minus 1 more or less is the same, okay? But okay, in any case, in this example, you have to unfold 3 cards, okay? In the unlucky scenario. Now, what about if you're using a quantum computer? So if you're writing a quantum algorithm to do the same. And the answer is that it is enough for you to unfold, to turn only 1 card. Regardless of the value of that card, the quantum computer knows exactly where is the joker. Okay? Now, you are going to tell me, no, this is impossible. And I also think that is impossible myself. Then if you apply all the mathematics that is coming from the quantum mechanics, you see that it works. Okay? But practically, it seems not intuitive. Okay? And so this is an example, just one example, to tell you why the behavior of quantum computer is not intuitive and why it is difficult to write programs that use them, because they are not intuitive programs. And so, by the way, if you, in any time, any moment, you want to interrupt me and ask me questions, please do it. So, before learning how to program a quantum computer, we need to understand how to build a quantum computer, or which are the building blocks that can be assembled in order to create a quantum computer. And so we need to talk a little bit, not too much, about quantum mechanics, okay? And so how many of you, I don't know, did study or did take a course on quantum mechanics or quantum physics? Okay. Good. So for you, what I'm telling now is really basic, okay? So in the world, there are, let's say, two types of objects, okay? Two types of experiences, okay? We have normal objects and quantum objects, okay? Normal objects are objects that follow the law of physics, okay? While quantum objects follow the law of quantum mechanics or quantum physics. Now, freely speaking, everything is quantum. It depends on the point of view, okay? So, a normal object, like, I don't know, a car. Okay, you have a car. The car is composed by mechanical parts. All of these parts follow the law of physics, okay? Traditional law of physics. The car itself, as an object, you can predict the position of the car if you know the velocity and so on, okay? So the Newton physics, or even if you introduce relativity, you have the law of relativity. But then you have also objects that follow the laws of quantum mechanics, and because normally we do not have a direct experience of these quantum objects, okay? So we do not have a direct experience of the law of quantum mechanics. For us, these objects behave in an almost impossible way, okay? But they do exist, but simply we are not aware of them, of these objects, okay? So where are these quantum objects? So how can we find them or build them, okay? Well, there are a lot of possibilities. So typically, a practical example is that very, very small objects, what I mean, if you take an atom, an electron, a photon, okay, you isolate somehow this small particle from the rest of the environment, okay, this single small object, okay, doesn't follow the law of Newton physics, but this object will follow the law of quantum mechanics. This is not the only way you can create or find quantum objects. You can also use superconductivity. So if you cool down some electronic circuits to a very, very, very low temperature, okay, very low, this superconductive circuit will follow the law of quantum mechanics. Just to tell you how low must be this temperature, it must be lower than the lowest temperature in the space. Okay, few, I don't remember, I think we're talking about millikelvins above absolute zeros, okay? So if you take the most remote point in the universe, it is too hot, okay? And we're talking about, I don't know, 0.5 kelvins above, so there are techniques, there are refrigerators that are able to cool down a circuit so that the circuit behaves be according to the law of quantum mechanics. There are other ways you can build quantum objects, okay? So a quantum computer is a computer that is composed by quantum objects that we call qubits, quantum bits, okay? And these qubits, these quantum bits, they follow the law of quantum mechanics instead of the law of Newton physics. Okay, so in a quantum computer, we perform computation by manipulating these quantum bits or qubits. So, which are the principle, the law of quantum mechanics that make qubits or quantum objects strange and powerful from the computational point of view? Okay, so now I will start a 2 minutes overview of the laws of quantum mechanics. Not all of quantum mechanics, but only the high-level points that are useful for us. So the first principle that it is really useful for us, is important, is called superposition. Now the typical classical historical example of superposition is the famous Schrödinger's cats. I don't know if you know the story of Schrödinger. Was this famous physics in quantum mechanics. In order to explain the idea of superposition, he described a conceptual intellectual experiment in which, in this experiment, he was saying, okay, you take a box. Inside this box, you put a cat and a venom, okay, and the venom can, in some probabilistic way, the venom can kill the cat, okay. So, if all this setup follows the law of quantum mechanics, the cat within the box is both live and dead. Okay? It's not a probabilistic point of view. It's not that is, could be dead or live and simply we don't know. It is both live and dead. Okay? So the example was not, it's a little bit cruel on animals. But, so I want to try to show you this principle with another intellectual example in which we need a laser or a light source, and we need polarization filters. So now suppose we have a laser which is emitting photons, so light, which is hitting this screen there, okay? You know that light is composed by photon. These are strange quantum particles, okay? And that can be considered as particles or as waves, okay? And if you think about photons, if you think of photons as waves, these waves, they have some directions, okay, in the space. We call this direction polarization of the wave. Okay, so normally when any type of light source is emitting photons with any kind of polarization. So you have a photon with a polarization in one direction, and then a photon with a polarization in another direction, and so on. So that you have a lot of photons that are, covering all the possible values of polarization. Now, within the path of the photons, we insert a filter, a Polaroid filter, the classical filters that are used in pictures by professional photographers, also by sunglasses, by the way. Okay. And this filter is such that it stops all the photons with the exception of the photons that have an horizontal polarization. So only the photons that have waves that are waving around the horizontal axis are able to pass through. So what is going to happen is that the intensity of the light that is hitting the screen will be reduced. Now, what if we insert another polarization filter that is stopping all the photons with the exception of the photons with the vertical polarization? What is going to happen to the screen? We have no light at all, because the first filter is letting pass through only the photons with the horizontal polarization. The second filter will stop the photons, all the photons except with the one with the vertical, but there are no photons with the vertical polarization, okay? Up to now, nothing strange. Now, what if I insert between the two filters a third one, which is 45 degrees tilted? So this last filter is blocking all the photons except the photons with the diagonal polarization. What is going to happen is that the light is able to pass through the three filters. Is it intuitive, this behavior? No, it's not intuitive at all, but it is, okay? And this happens because of the superposition of the photons because of quantum mechanics principles. So I will try to give the mathematical description of why this is going to happen, okay? And this happens because a photon, even if a photon is polarized along the, I don't know, the horizontal direction, it's not only polarized along the horizontal direction. It's a little bit on the diagonal, upper diagonal, lower diagonal. It's like the cat, okay? The cat is both dead and alive, and the photon is both vertical, horizontal, is a little bit of everything, okay? And going back to the Schrödinger experiment, so the cat is both dead and alive. But frankly speaking, when we see cats, did you ever saw a cat that is both dead and alive? No, never. Okay, because we are not quantum objects. So we are classical objects. So when you look at a cat, when you measure a qubit, okay, in the moment that you look at the cat, in the moment that you measure a qubit, that quantum object, we say that collapse. That means is not in superposition anymore, okay? In that moment, the quantum object the cat is either dead or alive. So from that moment on, the superposition does not exist anymore, okay? Because the act of measuring something this action is interfering with the quantum object. So the same is when you put the screen. In that moment, the screen is measuring the photo. Yes? I will later show you some scary mathematical formulas that will show you why does it happen. So this is the first law that we are interested in. The second law is that is called entanglement. Entanglement is the property, I'm trying to simplify here this principle, is the property of two quantum objects of being correlated regardless of their distance. So I'm trying to make another example. Suppose we have two coins, okay? And we put these two coins into two boxes. And we suppose that these two coins are quantum coins, okay? We put them in two boxes, and so when the two coins are in the two boxes, they are in superposition because they are quantum coins. So each coin is both head and tail, okay? Simultaneously. And only when we open one of the boxes, in that moment, the coin becomes head or tails. This is important. I will state this out more and more. Superposition is not the fact that we do not know if the coin is head or tail, okay? So if you are using this, if you are using a normal coin, you put the coin in the box, you shake the box, okay? As coin are not quantum coins, okay? Inside the box, the coin is either head or tail, and you simply do not know if it is head or tail, okay? But if you have a quantum coin, the coin is both head and tail. This is strange. Okay, now we have these two coins. You put it in the box, you shake the two boxes, and then you take one of the coins on on the moon or in another galaxy, okay, hundreds or millions of light years away from here. Then you open one of the boxes, and in that moment, the coin decides to be head or tail. In that same moment, the other coin in the other side of the galaxy decided to become head or tail. Okay, so the two coins are correlated in such a way that when you measure one of the coins, when you measure one of the qubits, your measurement, your act of reading the value of a qubit will instantaneously influence the value of the other qubit. Okay. Now, please ask me the classical question. Yes?
Can we have above light speed communication then if we...
Okay, thanks for asking me. Nobody never asked me this question. So I'm repeating the question for everyone. Can we use this principle to have faster than light communication? The answer is no. Why? Because, now let's start with this example of the two coins in the two boxes. In order to create entanglement, the two qubits, the two coins must be close by. Okay? Then I have to move one of the two in the other side of the galaxy. And the movement of this box takes, so when I move the qubit, I have to respect the law of general relativity. So I cannot move the qubit faster than the light. Okay? So I cannot communicate faster than the light. It is possible to, so this is a very informal, let's say, explanation. It is possible to do a formal mathematical explanation that is showing you that you cannot transmit useful information, okay, at all. So you cannot do communication faster than light. So superposition alone is able to give you an incredible speed up in quantum computers, okay? If you pair it with entanglement, you have even more powerful capabilities in your quantum computer. So quantum algorithms typically take advantage of superposition and also entanglement in order to be faster than classical computers. There are other principles, two principles that can help us in building fast and algorithms. Another principle is called tunneling. Tunneling is the ability of a quantum object of being in different points of space simultaneously. So you have, if you take a photon or an atom or an electron, you cannot know the exact position of these quantum objects, not because you don't know its position, but because this quantum object is not in a specific position of space. It is, the position of the object is a probabilistic position, okay? And this concept, which applies to physical space, applies also to logical values. Now, suppose you want to solve an optimization problem. You want to find the minimum of a very complex function. Maybe you want to minimize with the gradient descent a machine learning model, okay? Your optimization function is describing a landscape with a lot of valleys, okay? And you do a quantum gradient descent, okay? And you reach the bottom of a local valley. You are stuck there. I mean, if you're using classical techniques, the risk is that you are stuck in a local minimum. Okay, so you have to use tricks to try to explore, to exit from local minimum. If you are using a quantum computer, when you reach a local minimum, so you are in a local valley, you are not only in that valley, you are there, but with some probability, which is not zero, you are also somewhere else in the state space, in the landscape of your function, okay? So you are on one side of the mountain, but you are a little bit also on the other side of the mountain, okay? So if you're implementing an optimization algorithm and you reach a local valley, you are able to jump on the other side of the mountain and see if you can go even lower, okay? So tunneling is helping us when you write optimization algorithms in order to avoid to be stuck in local minimum. It doesn't work always. I mean, you do not have the guarantee that you are able to explore all of the space. So it works well when two valleys are not too far from each other, okay? It is a useful principle. Then we have the bad principle, our enemy, okay? Decoherence. Decoherence is the fact that quantum objects, so also qubits, which are quantum objects, tend to lose their quantum properties. Why? Because typically they do interact with the external environment. What does it mean to interact with the external environment? It could be because there is an X-ray coming from the sun, which is hitting your photon or your atom, okay? Because you are walking in the room and the vibrations interfere with the quantum, with the qubits, and they lose their quantum properties. What does it mean? That they lose coherence and they lose superposition. And if you lose superposition, you lose also entanglement and so on, and you lose all of these nice properties that allows you to do superpowers in computation. Okay. This is the biggest challenge in building quantum computers. Okay. So if you put all of this together and we try to a little bit more formalize a little bit more what is a qubit, okay? Let's do the comparison between a traditional bit and a qubit. Okay, so a traditional bit is some typically electronic device which is able to take two values, okay? Typically these are two energy levels, okay? And we conventionally call these two values, two energy levels, 0 and 1. You combine them, billions of bits, and you have a traditional processor. So inside this mobile phone, we have billions of transistors. Each transistor is able to flip between 0 and 1 state. Okay, okay. This is what you have inside any computational device, non-quantistic computational device. Now, what is a qubit? Well, a qubit is some device, electronic or physical device, okay, quantum device, which is able to take any of the infinite values on a sphere, on the surface of this sphere, okay? We conventionally call the north pole and the south pole of this sphere as 0 and 1, but theoretically speaking, the qubit can take any value on the sphere, okay? And why a sphere is too complex today to explain, so, okay. And so, theoretically, within a sphere has infinite positions. So, theoretically, you could save inside a qubit a number with an infinite number of digits after the comma, okay? With an infinite precision. So, if I ask you from the theoretical point of view, how much information can you theoretically store in a qubit? An infinite amount of information. Theoretically, there are some practical obstacles. So can you understand the power? In a bit, you can either put 0 or 1. In a qubit, theoretically, you can put suppose you have a vector of integer numbers, okay? A very, very, very long vector of integer numbers. You can transform this vector into, I don't know, a real number with a lot of digits, and you can store this vector regardless of the dimension of the vector inside a qubit. Okay? Which is the problem? The problem is that in order to store the information, or in order to retrieve the information, it takes a huge amount of time, okay? So one of the challenges that builder of quantum computers or designer of quantum algorithms are facing is how to store the information, how to practically take classical information and store it in the qubit in a short amount of time. And the opposite way, how to read this information, okay? So the first problem is called state preparation. It's a strange name, is a name used by physicists, but it means how can I put the information inside a qubit without taking forever, okay? And the second problem is called tomography, a strange name to say how can I read information from the qubit. So now, when you want to do quantum tomography, so when you want to read this information, what you do is that you sample, you do a statistical sampling of the information, which takes, you need a lot of samples in order to read the information. So you are losing all the advantages in the computational speed up, okay? So these are some of the challenges. But physically, how do you build a qubit? Okay. So from the practical point of view, if you take an IBM quantum computer or a D-Wave quantum computer or a Chimera quantum computer, which technology do these companies use to build quantum qubits? Well, there is still no standard technology, okay, to build a quantum computer. Companies are exploring different ranges of technologies. So the most used technology today is to use superconduction. So, cooling down to 20 millikelvins, okay? So superconductive qubits, so superconductive quantum computers are the most common quantum computers today. Why? Because from the engineering point of view, it is the simplest way to build a quantum computer, okay? There are companies that use single photons. You take a photon, you stop the photon, and the photon becomes your qubit. Now, photons, they have these bad habits of traveling at the speed of light. It is a bad habit because, how can you stop something which is traveling at the speed of light? You put it between mirrors, very, very, very close by mirrors. So the photon is just, jumping up and down between these two mirrors. So you trap the photon. Okay. And the mirrors must be very small and so these are called resonance cavities, but, more or less the principle is this one. Okay. So you trap the photons. And normally these qubits, they do not need to be cooled down, but you need to cool down when you want to read the qubit, when you want to read the state of the qubit. In order to read, to be able to detect, to measure one single photon, the single photon detector must be a superconductive device, okay? But you don't need to cool it down till 20 millikelvins. 1 Kelvin is enough. You may think, okay, but 1 Kelvin is still cold. Yes, but believe me, cooling down something to 20 millikelvin is possible, but it takes a lot of stuff. I will show you all the size of a refrigerator to cool down something to 20 millikelvin. Well, to cool down something to 1 Kelvin, it's easy, okay? You can use electrons, you can use atoms, you can use ions. If you're using ions and atoms, typically, you do not need to cool down anything, but you need vacuum. So you need to create small chambers with almost perfect vacuum, okay? And you have to stop an atom and you have to stop an ion. And again, atoms, they have this bad habit of oscillating, moving around because of thermal noise. So how do you stop an atom? You use laser beams. So you fire photons to the atom, and in such a way that the atoms stay still, okay? And you can use diamonds, so you insert impurities into diamonds. You create cavities within diamonds. And these cavities, if properly designed, behave as quantum objects, okay? And diamonds are nice because you don't need to create vacuum, you don't need to cool down anything, and you can you can buy a quantum chip and use as a gift in a ring. And there are other technologies, okay? And I will come back to these technologies later on. So this is an IBM quantum computer. It's an old model. Old means, I think it's 5 years old, okay? So it is prehistorical in terms of quantum computing. Do you see that it's not resting on the floor? It's hanging from the roof. Why? Because vibrations, okay, are dangerous. So this is a superconductive quantum computer. What you see here is not a quantum computer. What you see here is the refrigerator. Okay? If you open this refrigerator, inside here, this is the quantum computer. And truly speaking, the quantum chip, the quantum processing unit, okay, the quantum processing unit is here at the very bottom, a small, okay, set of electronic circuits. All of these you see up there is to cool down and all the electronics to control it is the standard electronics that is necessary to control the quantum processing unit. It is a really ugly machine. This is the IBM quantum computer. This is the first traditional computer ever installed in Italy. It was ugly, okay? So hopefully, with time, in the future, we will have small, nice quantum computers, okay? But we are more or less in the same period. And in any case, today, there are companies that are able to pack this quantum computer. This is a D-wave quantum computer. It's still a superconducting quantum computer, but they are able to hide all the ugly refrigerator machine inside a nice-looking box. So you are more happy to spend millions of euros if you buy this one, okay? And, okay. So this is the landscape, the today landscape of technologies used by quantum computer companies. So you see that almost 1/3 of quantum computers available on the world are superconductive. There are more or less 20-25% are based on photons, on electrons. These are based on electrons. There are 20% which are based either on atoms or ions, which are two variants of the same technique, and other techniques. You see how many companies are building quantum computers? Okay? It is something that typically we do not know. Okay, not all of these companies they have the same maturity. Okay. Some companies are just building the prototypes which are not yet available for general use. Okay. Other companies are already selling their quantum computers. For instance, AWS, they have a huge lab where they started a few years ago with the idea of building their own quantum computer to use in the cloud. Okay. Because they think this is going to be the future of cloud computing, to use QPUs, so quantum processing unit, to accelerate computation. As today, we are using GPUs to accelerate computation. And we're in Europe, and I'm proud to say that there are a lot of European companies So we are not lagging behind. There are many companies from North America, from Asia, but also from Europe. Is there a question? Yes? So the question is, if there is a reason why some technologies are more popular than other technology, more or less yes. Okay, so superconducting is superconductive. The properties of superconductive circuits are well known, have been well known for many years. Okay, and superconductive techniques have been used in the past to do other things. Okay, so there is a consolidated engineering knowledge on how to create superconductive circuits, because superconductive circuits have been used in the past to do other things. Okay, think about I don't know, maglev trains that are able to instead of using wheels, they are able to fly over superconductive magnetic materials. Okay, so superconducting technology has been used also for many other things. So there is a lot of, now you can buy, if you want to buy a refrigerator to cool down something to 20 millikelvin, you can buy it. I mean, there are companies that you just, okay, you order your refrigerator, you buy it. Okay, maybe it's not cheap, but it is a standard technology. Okay, while how to stop an atom, okay, is something that has been invented with the purpose of building quantum computers. Because before the idea of stopping atoms to build a quantum computer, no one ever tried to stop an atom. Okay, so there was the need to create all the surrounding technology that is required in order to stop an atom. Okay, so some techniques. I want to give you another example. Do you see topological material? Microsoft is the leader nowadays on topological qubit. What does it mean the leader? It's probably the only company that has been investing on this. Because these topological qubits, they follow an hypothesis about a type of qubit which are not macroscopic. They are macroscopic qubits, not small qubits. Are based on these are called the Majorana qubits because they have been designed on paper, okay, from the theoretical point of view, but an Italian researcher called Majorana. But no one has been never able to demonstrate that they do exist, because these topological qubits do not exist in nature. You have to build them, okay? And Microsoft has invested a huge amount of money to try to build Majorana qubits. So they are building a new state of matter, a state of matter that does not exist in nature. Okay, so this is why it is challenging. You have to demonstrate that something that has been designed only on paper is also really available. There are researchers that are still few years ago, I'm coming to that. They were questioning if Majorana qubits were possible or not. And even Microsoft, they published a paper 2 years ago saying, okay, we have been the first in the world to create a Majorana qubit. And then it came out that there were errors in their experiment. And so the Majorana qubit didn't exist. Then they worked again for an year, and now they came out recently, a few months ago, with the first real now evidence that Majorana qubit can be created. Okay, so some of these techniques are really frontier techniques. If you put all of this together, okay, you choose a technology, you put these qubits together, okay, and so if you take n qubits together, from the theoretical point of view, if you have a quantum processing unit with n qubits, you are able to obtain a speed up of 2 to the power of n. So while with the traditional computer, the computational power is linear with the number of bits, with a quantum computer, the computational power is exponential with the number of qubits. Okay? And this is the power of quantum computing. If you have a computer, a quantum computer with 20 qubits, you are able to perform 1 million of operations in parallel. Okay? Think about the degree of parallelism. You are able to do this in principle, in theory. Okay? Then there are some difficulties when you write the algorithm. Okay? While with the traditional computer, if you have 20 bits, you are able to do 20 operations, 20 binary operations in parallel. Okay? This is why we need billions of transistors within a normal CPU or GPU. Okay? Because if you take a GPU and you want to have access to a huge parallelism, you need a huge number of transistors. Okay? Okay. Now, we are almost at the point where I'm finishing the funny things, and we are going to start the difficult part. So, when you build a quantum computer, it's not only a matter of choosing the technology that you use to build the qubits. You can also you have choices also in the computational model that you can use, which are let's say the principle and the computational model that you implement in your machine, so that you can write algorithms that can do something useful. Okay, so this is a simple map of the different technologies or computational models that you can use. And it is a mixture of commercial brands and computational models. So I think I have an animation, I'm not sure. Okay, so these two computational models, gate-based and measurement-based, are two examples of quantum computational models, which are called universal. What does it mean? That it means that with this computational model, you can write any algorithm and solve any problem, like the von Neumann model. Okay, this computational model are the equivalent of the von Neumann machine. Okay? The most 99% of quantum computers follow the gate-based computational model. With these computational models, when you write a quantum algorithm, you need to write instructions, one instruction at a time. So one operation at a time. So it is a sequence of instructions where you tell to the computer, do this, then do this, then do this. Okay, like it's a little more intuitive, probably. But you have also analog computational models. Okay, like kind of analog computers, where you have your quantum computer, and there are a number of parameters that you can tune in this computer, and then based on the parameters, you're able to solve different problems. Okay, and then the quantum computer evolves in an analog way. Okay, not because you are controlling step by step the action of the computers. Okay, you do not control the actions, but you know that at the end of this evolution, the quantum computer will be in a state, so the qubits will be in a state that if you read these qubits, you have the solution of your problem. Okay, so initial configuration. So what do you do with this analog quantum computer? You set up the initial configuration, you click play, okay? The quantum computers work by itself, okay? You have no control on what is happening. The only thing you know that at the end, you have the solution to your problem, okay? And some of these analog models are still universal, okay? So you can solve on paper any type of problem and algorithm. So the adiabatic quantum computing is an example of an analog quantum computing model that is universal. There are some, let's say, simpler architectures which are analog. They are not universal. okay? So you cannot solve all the problems. And the focus of the second part of the today tutorial, so the part that is happening after the coffee break, will be on the analog part. Why? Because it is much easier to understand, okay? And more specifically, we will focus on a technology that is used by this company, which is D-Wave, okay? Why do we focus on this technology? Not because D-Wave is paying us money. I would like, but they're not paying us money. It's because it is the simplest technology, quantum technology available today. The simplest and the cheapest, okay? So if you want to start playing with a quantum computer, it's a good way to start with. Okay. But, okay, before we focus on this part, you will have to be patient, because I want to give you some introductory concepts of gate-based approach and adiabatic quantum computing. So gate-based, why do I want to tell you something about gate-based? Because the future is not with analog quantum computing. The future is with gate-based technology, okay? So with the exception of a few companies, all the companies that you saw in that map are using a gate-based model, okay? And I will spend a few words also on the adiabatic quantum computing model, because it is a bridge to better explain the behavior of the wave, okay? So, okay. I mean, it's not, the mathematics is not complex. The notation is ugly. It's not ugly, it is strange, okay? So I told you that qubits can take any of the infinite values on a sphere, okay? And in order to represent qubits, that is points on this sphere, we use a strange notation. It is a vector notation, okay? So you use vectors of complex numbers to represent the value of a qubit on a sphere. And instead of using all these vectors, okay, we use a compact notation to simplify, okay, the writing. Do you see this very strange notation here? This is called the bracket notation. Okay, it is a compact notation to simply represent vectors and matrices of complex numbers. Because when you write, from the mathematical point, when you write an algorithm for quantum computers, you have to use these vectors and matrices of complex numbers, a lot of them, okay? This notation is called the bracket notation or Dirac's notation, okay? So typically, you use, you see this the red circle, okay? This is called a ket, okay? And it is a notation that is used to represent column vectors of complex numbers. This is called, the second element there is called a bra, and it is used to represent row vectors of complex numbers. These are not just vectors, they have some properties, so the norm of the vector must be equal to 1 and so on, okay? There are some other properties. Then you can combine this notation in order to represent mathematical operations between vectors, or between also vectors and matrices, because at the very end, when you write a quantum algorithm, it's a matter of combining products of vectors and matrices at the very end, okay? So, with this notation, you are performing the scalar product between a row and a column vector of complex numbers, okay? With this notation, you are multiplying a column vector times a scalar, A. A is a scalar. It is complex, okay? Remember that all this notation is about complex numbers. with this notation, you are multiplying, you perform the product between a matrix M and a column vector. And with this notation, you are multiplying a row vector times a matrix times a column vector, okay? So, from the mathematical point of view, we are not performing strange operations. The notation is strange, and if you are not used to the notation, it's really difficult to understand the mathematical formulas, okay? Do you have questions up to now? So at the very end, writing a quantum algorithm is a matter of using this notation to perform a number of products, okay? So, given this notation, let's start to see how do we mathematically describe the behavior and the properties of one single qubit, okay? So we start to describe one single qubit, and then we will see how do we describe the operations that we can perform on a single qubit. Then we will see how to describe multiple qubits together, which is a little bit strange. Why it is strange to describe multiple qubits together? Do you remember? Well, which is the useful property when you have two qubits or two quantum particles? Entanglement. Because of entanglement, okay, the description of two or more qubits is peculiar. And then we will see how to describe operations on group of qubits. Okay. So this is the laser example. Okay. I'm going back to this example because if you take a photon, okay, a photon is a quantum object. A photon can be used as a qubit. Okay. So think about a photon and its polarization. Now, suppose we have a photon with a generic polarization, okay? How can we describe the polarization of this photon? Well, we can describe the polarization of this photon as a linear combination of two orthogonal polarizations. So if you have a photon with a polarization along any generic direction, okay, you can say, okay, now suppose V is this column vector, this qubit, okay, that describe a generic photon, okay? Well, we can say, okay, this the generic polarization is an horizontal one with a coefficient and a vertical one with another coefficient, okay? So this is the mathematical way we use to represent a qubit, one single qubit, okay? So in this example, a diagonal photon, so a photon with a diagonal polarization, is represented in this way. Okay. This quantity A and B, remember, we are in the area of complex numbers. They are complex numbers. Okay. And we call these quantities amplitudes of the qubit. So a qubit has two amplitudes, which are two complex numbers. Okay. And the norm of these amplitudes must be equal to 1. So the square of A plus the square of B must be equal to 1. Yes. Well, when you, yes, the square is a complex one. Yes, exactly. So if both A and B are not 0, the qubit is in superposition. What does it mean to be in superposition? Exactly. The qubit is both horizontal and vertical. It doesn't mean that it is horizontal or vertical and we don't know. It's both horizontal and vertical. Okay? It's not diagonal. It's both horizontal and vertical. And when we will measure the qubit, in that moment, the qubit will become horizontal or vertical. And how do we measure a qubit? You put a filter, a polarization filter. If the qubit is able to pass, then in that moment it will become, I don't know, vertical or horizontal. Okay. So the square of A and the square of B are telling you which is the probability when you measure the qubit for the qubit to be horizontal or the probability for the qubit to be vertical. Okay. Of course, when you, from the practical point of view, when you are using quantum computing, we are not using vertical or horizontal. We want to use 0 and 1. Okay? So the only important thing is that these two vectors that are used to describe a qubit, these two vectors must be orthogonal and orthonormal. So the two vectors must have norm 1 and must be orthogonal. Okay? You can choose any pair of orthogonal vectors to describe a qubit. Okay? So typically, so this is the mathematical demonstration of what happens. Okay? I think we are running short of time, so I will skip this mathematical demonstration, and if we have time, I will come back to here. This is the mathematical demonstration to show you why, when you insert the 45-degree Polaroid filter, the light doesn't stop. Okay? So from the practical point of view, instead of talking about vertical and horizontal, we typically use two orthogonal vectors that we, by convention, we call 0 and, oh, this is an error, this is a 1. Okay? So this is 1, okay? So we call this 0 and 1, okay? These are two column vectors of two elements, 1, 0 and 0, 1, okay? These are orthogonal, okay? So typically we describe a qubit as a linear combination of these two vectors. We call this vector basis, okay? Like the bit 0 and the bit 1, okay, are the basis of the digital computer. These are the basis of a quantum computer. Okay, so and these are, but this is not the only possible choice of basis. Okay, so these are standard, are called the standard basis, because by convention we associate to basis 0 the binary value 0, and again by convention we associate to this basis 1 the binary value 1. Okay, it's just a convention, but you can use any pair of orthogonal vectors. So if you are going in the future to write quantum algorithms, you will see that very often you use also these two bases, these two vectors, which are by convention represented with this symbol, plus and minus. Okay, these are orthogonal vectors, but and these are called Hadamard bases. Now, whenever you measure a qubit, so if you have a qubit which is described by this vector up here, normally the qubit is in superposition, so A and B as different from 0. Whenever you measure the qubit, the outcome of the measurement will be either one direction, horizontal, or vertical. Okay? In that moment, so if you measure the qubit and the qubit is vertical, A will become 1 and B will become 0. Or the opposite, if you measure the qubit and the qubit is horizontal, B will become 1 and A will become 0. So in that moment, when you measure the qubit, you lose the superposition. Okay, it is an irreversible operation. Okay, and this is an axiom. Okay, it's because in the reality is telling us that this is what happens. When you measure quantum objects, you lose superposition. So another important strange thing is that superposition depends on the basis. So the fact that a qubit is in superposition is not an absolute property of the qubit. If I'm going back a few slides. Now, suppose you have a photon, one photon, which is in 45 degrees diagonal. Okay? If you want to measure this photon by using an horizontal and a vertical filter, okay, that photon will be in a superposition of vertical and a superposition of horizontal. But now suppose that instead of using an horizontal and a vertical filter to describe this photon, you are using two orthogonal filters, which are rotated by 45 degrees. Okay, the photon is exactly the same photon. Is a photon with a 45-degree polarization. Now you describe it as a linear combination of two diagonal polarization. Is this photon in superposition now? No, because the probability for that photon to be in one direction is 100%. Okay, so this is a strange thing. Superposition is a property of how you mathematically describe or how you measure the qubit. Okay. So, and this is something that I already anticipated to you. Superposition is not the fact that we do not know the state of a qubit. Superposition is the fact that the state of a qubit, so very often we think that quantum computers are probabilistic. No, they are deterministic. So all the computation of a quantum computer are perfectly deterministic. The probabilistic problem arises when you measure the qubit. So when you read the value of a qubit, in that moment, you have a probabilistic behavior. Okay? So superposition doesn't mean that, okay, we don't know, the qubit is either A or B, is either vertical or horizontal. No, the qubit has a very deterministic behavior. Simply, okay, when you measure it, you affect the behavior of the qubit in a probabilistic way. It is impossible for us to know the value of A and B. It is impossible. You do not measure A on B. So when you measure a qubit, you simply know vertical or horizontal. Is it vertical? Yes. Or is it horizontal? Yes. Okay. That's it. Okay. It's like when you put a filter. So measuring the qubit is like putting the filter. You put a filter and you have only two possible outcomes. The photon is able to pass through or not. So you know if the photon is 0 or 1, vertical or horizontal. Do you know the probability of the photon to be horizontal or vertical? No, you don't know. Because if you know the probabilities, you know A and B. Do you remember when I told you that even if a photon, a qubit, can take any of the infinite values on the sphere, the challenge is for us how to read this value. If you are able to know A and B, you know the exact position of the qubit on the sphere. And you will be able to put an infinite amount of information in the qubit, which, I mean, the theory is telling you that you can, but if you want to know A and B, you need to do what is called the sampling, the quantum tomography, which you need to put a huge number of, you need to repeat the same algorithm again and again. Now, suppose you want to know A and B. You write a quantum algorithm, you run the algorithm, and then you want to read the A and B of a qubit. How can you read A and B? The practical approach, I'm simplifying a little bit, but this is what happens, okay? You have to run the algorithm a huge amount of times. Every time you read and you sample the result. And you will, I don't know, for 90% of the times, you will obtain vertical. For 10% of the time, you will obtain horizontal. Then at this point, you know A and B, okay? But it's not, it is a probabilistic measurement, okay? So A and B, they do have an exact precise value. Simply, we cannot measure it. We can only sample A and B with a finite precision. Suppose you have a qubit, which is a point on the sphere, okay? And the point of the sphere is uniquely described by A and B, which, remember, are complex numbers, not real numbers, okay? So if you know A and B with infinite amount of precision, you know exactly the point of the sphere. The problem is that it is impossible for us, okay? So you do a large number of, so if you're able to perform an infinite number of experiments, which takes an infinite amount of time, you're able to perform a sampling of vertical, horizontal, and based on the proportion of vertical and horizontal, you will know exactly A and B. But this sampling will take an infinite amount of time. So as we do not have an infinite amount of time, the accuracy of your estimation of A and B depends on how much time do you want to waste in sampling A and B. It seems that this is putting a huge limitation on the ability of the quantum computing to perform calculation. But truly speaking, this is a problem only for reading the final value. So now I want to give an example. Suppose you write an algorithm, a quantum algorithm, which is computing at the end a qubit. Okay? And then you are not able to read this qubit. You are not able to read this qubit with all the precision that you want, unless you waste a lot of time. But then you can take this qubit and use it as an input to a second step. And then you can use the output of a second step as an input to a third step. Okay? So you still have value. You concatenate a number of phases, and maybe at the end it only cares for you to know 0 or 1. Okay? So it is a limitation. Yes, it is a limitation. But for some application, it is a limitation, and researchers are working on how to reduce the complexity of reading A and B. Okay? But in the meantime, while reading A and B is still challenging, okay, you can still have a value by this because you can use the output of a quantum computation as an input of a second phase and so on. Okay? I want to make you an example. Suppose you have a classifier. In a classifier, the only things you care is that the output is either 0 or 1. Okay? But by me, in order to arrive to this final classification, you need to perform a huge amount of computation with a lot of data, a lot of real values. Okay, all these steps can be done by qubits. Okay, so at the end you need only 0 or 1. Okay, so I understand it's not easy to grab these. Believe me, I'm trying to compress in half an hour something that it takes 1 semester to explain to my students. So yes.
How does the choice of the basis relate to how you measure?
No, the choice of the basis it doesn't influence the accuracy. So, because from the practical point of view, as we are classical, and we do computation by using classical computers. At the very end, we need 0 and 1s. Okay, 0s and 1s. So typically, we choose a set of bases, these standard bases as a frame of reference, and we give to these two bases the classical values 0 and 1, because at the very end, when you read something, you need to read something in terms of 0 and 1. And so the output is always measured by using standard bases. Within the computation, it could be convenient for you, but only from the mathematical point of view, to use a compact notation. It could be convenient for you sometimes to introduce other bases, but simply for you to better understand what is happening. So the choice of bases that you use when you write your algorithm does not affect the final result, okay? Because from the interface between classical and quantum computer, we always assume that this interface is done with standard bases. Yes?
Do we have problems with errors though? Because now it sounds like it's all deterministic, and like we just repeat the experiment, and then we just have like the normal statistical error bars, I guess. What happens if there is a vibration during our experiment? Does it like collapse? And
it's a good it's a good of questions. Okay, this is a very good question. There are two probabilistic effects when you let's say perform computations with a quantum computer. One probabilistic effect is in measuring. Now, suppose you have an ideal, perfect, error-free quantum computer, okay? This quantum computer is going to be deterministic in its behavior, okay? The only probabilistic issue is when you provide the input or when you provide already the output, okay? because of this problem that you cannot measure A and B directly. But then, real quantum computers, they are affected by behavioral errors, okay? Because of decoherence. Do you remember I told you decoherence, okay? So there could be unpredictable behaviors during the computation because there are errors. And this is the biggest limitation of current quantum computers. The probability to have an error during the computation increases with the duration of the computation. So if you write an algorithm that is very long in its duration, long means, I don't know, half a second, it's too long, okay? Because the probability to have an error, the probability for a qubit to become decoherent, to collapse, okay, is large at this point, okay? So how do we solve these problems of this problem of errors, physical error in the computation? There are two approaches. One is done by vendor of hardware. So the hope is to build qubits which have an error correction capability. Okay, well, this is the same that happens with traditional chips. Okay, even traditional microchips, they do have errors. Okay, in their behavior. There are some techniques that use redundancy in order to correct this error, to detect and correct these errors. Okay, is it possible to do the same with quantum with qubits? Yes, but it's incredibly difficult. And we'll see why. Okay, one of the reasons why it is so difficult to do quantum error correction is because you cannot copy a qubit. Can you copy a bit? Can you copy a number in a normal computer? Yes, you can write A equal to B. You copy B and you put B into A. Can you copy qubit B into A? No. It's impossible. There is a law of quantum mechanics, it's called no cloning theorem, that states that you cannot copy a qubit. And so, can you imagine how it is difficult to do quantum error correction without the ability to copy qubits? Okay, so it's not impossible, but it's difficult. Okay, so builders of quantum computers are already producing qubits. They are called logical qubits, where you put together physical qubits affected by error in such a way that the logical qubit has no error. But do you know how many qubits, physical qubits, up to today you need on average in order to have a logical one without errors with the current technology? You need, I don't know, roughly speaking, the order of magnitude, 1,000 qubits, physical qubits, in order to have a logical qubit that has no error. Okay, this is the state of today's technology. This technology is improving. Okay, so let's say the hope and the path is that in the future we will need less and less and less physical qubits in order to create a logical one that has no error. But this today is the largest limitation. Another possibility for you is to rerun the algorithm. So if you are using a quantum computer which with qubits that are affected by errors, you rerun the algorithm again and again and again, and you compute some statistical distribution in order to see if there are outliers and so on, in order to compute the exact solution of your algorithm. So there is a whole area of research of writing quantum algorithms that assume that when you run an algorithm, the output of your algorithm will be affected by error. It's called noise, this type of error. Okay, is today, I don't know, in 5 years, probably, hopefully, we will have quantum computers without noise. Okay, and so it is a kind of transient problem today. Okay. So now we know what is a qubit, and we know the challenges in reading or writing qubits and so on. Now, but in order to write an algorithm, we need to be able to perform some mathematical operations on qubits. Okay, so if you have a bit, which type of mathematical operation typically you can perform on a bit? You can apply some logical gates, AND, OR, XOR. So you can you have gates that are able to take a bit and transform this bit, or you can take, you have gates that can operate on 2 or more bits and perform operations, okay? So the same is with qubits, okay? We can use gates to take a qubit and transform its value, okay? So if you use a gate that is operating on a single qubit, this is called a single qubit gate, okay? From the mathematical point of view, a gate is simply a 2 by 2 matrix. So performing an operation on a qubit is simply a matter of multiplying this matrix by the qubit, okay? So a real quantum computer has a number of physical gates that are able to apply operations on a qubit. And these are just matrices, okay? So when you write, if you want to write an algorithm which is using a single qubit, writing your algorithm is simply a matter of performing a sequence of multiplications of matrices times vectors, okay? So these are examples of gates that you can apply to qubits, okay? These are the most common single qubit gates that you will meet in quantum algorithms, okay? Each of these gates transform a qubit in such a way that there are some nice properties that, or some nice effects that happens, okay? We do not have the time to see why these gates are important, okay, and what do they do. And so when you write an algorithm, a quantum algorithm that is using only one qubit, you use this graphical representation, okay? This means that you take as an input a qubit. Oops, oh my God. You take as an input a qubit, you apply gate A, you apply gate B, and you have as an output this qubit, okay? This is, so when you write an algorithm, you simply, you can write an algorithm instead of using, I don't know, pseudo languages, you simply design these diagrams, okay? And you can extend this to, no, I do not have a diagram. You can extend this notation to multiple qubits, okay? I'm sorry, I do not have a diagram to show, but writing a quantum algorithm is simply a matter of designing this diagram, okay? This is a logical algorithm, okay? So it doesn't mean that your quantum computer as gate is able to perform gate A and B, okay? But it's not a problem for you. I mean, you write this algorithm, then when you compile the algorithm, now suppose you write an algorithm, a quantum algorithm, that is using, I don't know, gate S, okay, in the sequence of operations. Now suppose that the quantum computer you are using does not have gate S as a physical gate, okay? It's not a problem for you because the compiler will transform this gate into a combination of other gates that are available on the quantum computer, okay? Compiling a quantum algorithm is called transpiling, okay? So typically the transpiler will transform the gates that you are using in your algorithm into the gates that are available in the machine, okay? So it's not a problem for you. Yeah?
Is it just an approximation or is
No. Is so quantum. It is possible to demonstrate that if a quantum computer there is a minimum set of gates that are sufficient to represent all possible gates. So builders of quantum computers, they do provide their quantum computers with the minimum number and typology of gates such that all other gates can be not approximated, but can be described in an exact way, okay? So it's not a problem. It's not a problem for you. It's not an approximation. And before moving on, one last comment. about how do we describe multiple qubits together, okay? So when you describe multiple qubits together, you still use a vector, okay, of complex numbers. But if you have n qubits, you need a vector of 2 to the power of n numbers, okay? And this is why, and this is where you have the second power of quantum computers. Because if you have, I don't know, 10 qubits, the values, the behavior of these 10 qubits is described by a vector of 2 to the power of n numbers, okay? And if this vector has some properties, these n qubits are in entanglement, which means that you have this additional superpower of this additional computational superpower, okay? Describing the mathematical properties and why entanglement is useful is, we do not have the time, okay, today. And so this ends the introduction on the gate-based model, okay, which is, as I told you, the most universal possible way to do quantum computing. Now, before we reach the break, I want to introduce you adiabatic quantum computing, which is an analog, a type of quantum computing which is an analog quantum computing approach, okay, which will be used by Maurizio after the break to do a more practical session. So we are in this part of the map, and so here the idea is that instead of giving instruction to the quantum computer to execute a sequence of operations, we use the natural behavior of a physical system. So if you take a physical system, you put this physical system in a state of high energy, and you let this system evolve, the system will evolve toward a state of minimum energy, okay? So this is true also for quantum systems. So if you have a quantum device, you put this quantum device in a state of high energy, the quantum device will evolve toward a state of minimum energy. So if you are able to use parameters in this quantum device in such a way that the state of minimal energy will correspond to a solution of your problem, you are able to implement an analog quantum computer, okay? So the type of quantum computer we are dealing with is called adiabatic quantum computing, because the properties that make this quantum computing paradigm possible are true only if the evolution is slow. Adiabatic means slow, okay? So you put the quantum computer in a high energy state, you let the quantum computer evolve slowly, and at the end you have the solution. Please ask me the question.
What does slowly mean?
Okay, what slowly mean? I mean, we use quantum computing to run computation fast, and now I'm asking you to do things slowly, but this is slow from the quantum point of view, okay? So slow means, okay, in, I don't know, 20 microseconds, okay? This is slow, which is slow for the quantum phenomena, but it is fast for us, okay? And so the idea is the following. So this slow evolution is called the adiabatic condition, okay? And I think I have a picture here, a diagram that is helping us to understand the key idea behind this. Now, here we have two colors, okay? The blue line represents the function that we want to minimize, okay? Now suppose we want to solve an optimization problem, a minimization problem, okay? And suppose this is the shape of the final function we want to minimize. So we want to find this point of minimum, okay? This is the problem we want to solve, okay? And now suppose you have an n-dimensional problem. So finding this minimum is a nightmare, okay? And the green line represents the probability for the quantum computer to find this point of minimum, okay? Now, the key idea of adiabatic quantum computing is the following. We start we initially configure our adiabatic quantum computer in a state such that the probability to find the minimum is uniformly distributed. So if the landscape is an horizontal line, where is the minimum? Everywhere. Okay, so the green line is again a flat line, okay? Because the minimum is everywhere. We have a uniform probability of finding the minimum everywhere. Of course, this is not the solution to our problem, okay? How do we create this initial configuration? Well, with superposition, okay? A maximum superposition. You have a maximum superposition. So if you have a lot of qubits, if you have a maximum superposition, it means that the probability of having A, B, when you measure the qubit are the same, okay? Uniform distribution. Then you configure your adiabatic quantum computer in such a way that when the system evolves toward a state of minimum physical energy, the landscape will be that one, okay? If this evolution, so this represents the evolution, okay? If the evolution is slow enough, the landscape will start changing slightly, okay? The probability of being in one of the valleys will increase a little bit with respect to the rest of the configuration. And what is going to happen is that even if, now suppose this is the valley we are looking for, the valley here is not in the same position as here. They are in a different position. But if the evolution is low, this probability we will start finding a solution here, and then slowly, our solution will move toward the exact final solution, okay? I think I have another diagram that is trying to explain this problem, okay? Look at this, okay? We have the landscape, and thanks to this adiabatic evolution, the landscape is changing slowly, okay? So the ball is stuck in the valley, okay? So, and you start from a situation where you have only one valley, so you have no problem of being in a local minimum. There is only a global one. And then the landscape slowly will change toward the final solution. So there will be, at this point, a lot of valleys, but your ball will stay always in the valley with the minimum energy, in the global minimum, okay? So at the end, you will find the solution. This is what happens when you are using this adiabatic quantum computing, okay? Which is a universal quantum computer. You can solve any problem in this way, any problem. The problem is that adiabatic quantum computers do not exist. Quera is not adiabatic, no, okay. So they do not exist, okay? So we need to simplify some assumptions, okay, a little bit. And we introduce quantum annealers, okay, which are a different, they are parents of adiabatic quantum computers, okay? Instead of using the adiabatic theorem to stay in the local minimum, they use the tunneling effect. Do you remember when I told you about the tunneling? Okay, so with a quantum annealer, even if you are stuck within a local valley, even if you start in a local valley, your ball has some probabilities to be able to jump on the other side of the valley and then to the other side. So you're still able to find the global minimum, okay? There is a slight difference. Here you know for sure that you will find the global minimum. Here it depends on the shape of these mountains, okay? So this is why these are not universal quantum computers. And So from the mathematical point of view, how do you write an adiabatic quantum algorithm? Okay. Your quantum computer. So what you do is that you write. You need to describe the energy of your quantum system by using a function which is called the Hamiltonian. Why? Because in quantum mechanics they like to call the energy of a quantum system by using this term. Okay, it's simply the energy of the quantum system. Okay, and you write this energy, this Hamiltonian, as a combination of two Hamiltonians, a linear combination. The Hamiltonian B is at the very end is a matrix. Okay, this Hamiltonian is a matrix. Okay, with some parameters in such a way that if you minimize B, you are able to find the solution of your problem. Okay, the problem is that you don't know how to minimize B. Okay, because B, the Hamiltonian B, is describe a complex function with a lot of values. Okay, then you have another Hamiltonian A, which is a very simple Hamiltonian, where it's very, very, very easy to find the optimal solution. Very easy. Okay? Then the Hamiltonian of your system is a linear combination of A and B. And you start, you see there are two coefficients, coefficient A, coefficient B. You start with B equal to 0 and A equal to 1. If B is equal to 0 and A equal to 1, for you, it's very easy to find the minimum. Then slowly, you increase B and you decrease A. This is the only way you can control the evolution. How fast you decrease or increase the two coefficients. At the end of the evolution, A will be 0 and B will be 1. And because of the adiabatic theorem, you know for sure that the system will be in the solution of your optimal problem. Okay, optimization problem. So you do not compute this. You let the system compute it for you. Okay. So the trick here is how to describe your optimization function in terms of the parameters of this energy function that the quantum computer gives you to. So you have a number of parameters you can choose. Okay. What happens? So very typically, in most adiabatic quantum computers, most especially in the quantum computer, in the quantum annealer that Maurizio will show you after the break, we express the quantum computer is such that you can describe the energy as a quadratic unconstrained binary optimization problem, a QUBO problem. Okay, so the quantum computer lets you describe the HB, the energy landscape, as this. So, and which are the parameters that you can choose are the coefficient A and Q of the optimization problem. So, summing up, with this type of adiabatic quantum computer, this special family of adiabatic quantum computers, which are called quantum annealers, you can solve quadratic and constrained binary optimization problem using the speed and power of qubits. Okay, and you are not more or less, you will not stack into local minimum because of the tunneling effect. You will be able to jump always in the global minimum. Okay, so this is what happens in theory, but we will see that in practice, when you are using a quantum annealer, there are some tricks that you have to follow. One last slide before I let you free to take some energy. What happens if the evolution of your system is not slow enough? Okay. So normally, these lines describe the energy of your adiabatic quantum computer. Okay. So normally, you start with an initial configuration where you are in a global minimum, such that it's very easy to find this global value, the global minimum. Then you let the two coefficients A and B to evolve. Okay, the energy of the system will change slightly. At the end of the evolution, you are in the minimum of the new valley, the one that you are looking for. Okay, but there are a number of other valleys which are not global, local. Okay, and this is the energy of these other valleys. Okay, and it could happen during the evolution that the energy, so the objective function, okay, of your global minimum, global valley, and the energy of another, maybe far, far, far away, local valley, the two energies are different, but not too much different, okay? This could happen during the evolution. So if your evolution is too fast, it could happen that, I think I have an animation, I'm not sure. Yes, a kind of animation, okay. So this is the evolution. Well, it could happen that instead of going up and then down in your global valley, you jump to another valley, which is not the global one, it's a local one. Even if it is far away, even if the solution is totally different. And you do not realize that this has happened, okay? So this is why it is important for you to do this slow evolution, and this is why it is important for you to repeat this, the run of this algorithm several times in order to compare the solutions, because it could happen that you find a solution which is the wrong one. Okay?
Good morning, good second half of the morning, everyone. I am Maurizio Ferrari da Crema. I work with Paolo at Politecnico di Milano. So the menu for this session is going to be the following. I will spend a few moments playing around with a simulator of a quantum system that is provided by the IBM quantum platform. This is just a way for you to see to have a sense of the behavior of a couple of interesting operations and to see a very small example of something that one can do that was considered a particularly important result some time ago. Unfortunately, working with gate models requires to reformulate problems through linear algebra, which is something that is doable, but it's quite complex, so we will not go into that much of a detail on this part. Then we will go through a few formulations for optimization problems that are more relevant for our field, meaning we will see feature selection applied to recommendation systems, graph partitioning, community detection, this type of problems. And then I will show you how to use those, how to submit those problems to the D-Wave quantum annealers through a couple of notebooks that are available as part of the tutorial materials. So I will show you where they are. The link is on the tutorial abstract, but if you look for Quantum Clé on Google, you will find this website. This hosts the all of our activities on quantum computing applied for IR and recommendation. It's the website of the lab Paolo mentioned a while ago. We are organizing it in collaboration with Nicola Ferro and Andrea Pasin from University of Padova. There have been a few editions of it, and there you will be able to see examples of what we did, the infrastructure, the architecture, and various other information of this type. On the right, you will see a tab tutorials, at the bottom of which there's RecSys, and at the bottom of the page, after the outline of everything you'll be able to find the materials and the link to the repository with the notebooks. Since we don't have live access to D-Wave, unfortunately, I don't have an API key to give you, but you will be able to see the results of the execution on the notebook. The cells are all there, so we will be able to discuss the behavior of the systems a bit. Okay, so if you're interested in quantum computing, I encourage you to have a look at the IBM Quantum Experience portal. They have lots of tutorials and useful information on their proprietary architecture and their systems. They are building a framework with a number of tools that can be used for to write quantum algorithms and simulate them. It's called Qiskit. So they are a very active player in the field. There is a number of competitors here at play. Google has its own Cirque model, and a number of other companies are building their own architectures. So depending on what you need to do, you may want to look for alternatives. The nice thing is that they provide a nicely looking simulator. So what's happening here? At the top, we see a bunch of squares with colors and letters. Those represent quantum gates. There's a number of them. In the middle, you will see two horizontal lines denoted by Q0 and Q1. Those represent the qubits. And if I drag gates on there, I can simulate operations applied on the qubits. On the right, at the very end of this, you can see some statistics on the outcome of the measurement. For example, the first qubit has a blue circle. This means that at the end of this very simple computation, the state of that qubit is going to be 1. If I don't do anything, well, the state is going to be 0. Not surprising. Here at the bottom, you see the probability of reading each of the possible states. We have 2 qubits, so 4 states. For the moment, everything is in 0, 0. We're not doing anything at all. If I apply a simple negation, a NOT gate, on the first qubit, the state changes. As happens in a classical system, the first qubit becomes 1. If I apply a superposition, so a Hadamard gate, what happens is this. We have the circle split it in 2, gray and blue, meaning that we have a 50% probability of being in a 0 state and 50% in the 1 state. At the bottom, you see another visualization of the very same probability. So 50% to be in 0, 0, 50% to be in 0, 1. The second qubit remains 0, nothing is happening to it. What if I apply a 2-qubit operation to create entanglement? So, as Paolo discussed, entanglement is a form of correlation. It means that we are creating a relationship between 2 qubits that does not exist classically, and we can do it in a number of ways. This is the simplest form of entanglement, a superposition and a 2-qubit operation. What is the state of this system? If you look at the bottom, we have only 2 bars, 0, 0 and 1, 1. The state 0, 1 and 1, 0 do not exist. So we are creating a type of interaction between the 2 qubits that would not be possible to create in this form in a classical system. If we apply a measurement on one of the 2, we will have a value, 0. If we measure 0, we already know the state the second qubit will be in, 0. If we measure 1, we already know the state of the second qubit, 1. So this is a particular formal correlation. Now, playing with these concepts is not easy because if you want to go beyond very simple examples such as these, things become quite complex. But through the particular types of interdependencies that you can create between the states of the system, then you open a way to explore your solution space much faster than you could do classically. I want to give you a very small example of a super simple quantum algorithm. So here is what it looks like. We have a bunch of Hadamard gates. Those create superposition. And we have a NOT operation on the second qubit. These vertical lines do nothing. They are just a graphical sign to separate things in a way that looks nice. For the moment, our simple system only exists in a state where the first qubit is 0 and the second is 50-50. So 50% we will measure 0, 50% we will measure 1. What happens if we put something in between here? So if we add additional quantum operations, if we put a negation on the first qubit, nothing changes. The first qubit remains 0. If you put a negation on the second qubit, oh, nothing changes again. How about if we create entanglement here? If we put a 2-qubit gate that would normally create entanglement. Something has happened. The first qubit now is in state 1. Okay, What if we play around with this a bit? So what if we add a negation after it? Nothing changes. If we move the negation, oh, nothing changes. Oh, sorry. I meant to put it here. Again, nothing changes. Nothing changes. So what can happen in quantum systems is we have built a very simple entanglement detector. So we have built a very simple sequence of quantum operation in the middle of which we can put a function, and we can identify whether a function possesses a certain property. This was a very popular, let's say, the very first algorithm that shows a computational speedup. It's called the Deutsch algorithm. It's a whole lecture on a quantum computing course. So this I just gave you a very high-level sneak peek of what it does. But it was the first time where it was possible to show that with a simple quantum operation, I can take a function and know a characteristic of that function using only one operation. Whereas in a classical system, I would need to query its possible values and require two operations. So it was the very first proof of a quantum speedup. Now, this problem is extremely contrived, so it's unlikely that at any point in my existence, I will want to know whether a function has entanglement. But this algorithm was later extended to multiple qubits. It was extended to finding the period of a function, which was then extended into the Shor algorithm, which published in the 90s, is the algorithm that shows that through a quantum computer we can factorize numbers with a superpolynomial speedup compared to classical systems. So this very, very simple example was the first step on a sequence of developments that broke RSA encryption, on which most of our encrypted communication on which most of our encrypted communication relies on. And so since the 90s, companies that deal with secure data had to change encryption protocols to try and build them in a way that would be resilient to quantum devices. So oftentimes, it's a very nice field to work on, because you see that everything is being reinvented to leverage new paradigms. If you look around the platform, you will also be able to see lists of existing quantum computers. So, sorry, I wasn't able to change the language for some reason, so it's all in Italian. But here the list is IBM Pittsburgh, Kingston, Feds, Marrakesh, and such. They're all quantum computers. You can see some of their statistics. So, for example, the first column is, the second column is the number of qubits, so 156. All of them have 156, with the exception of the last two. And if you click on it, you'll be able to see some statistics. What I'm interested in particular is this image. This image represents a topology, so the way qubits are connected. Each dot represents a qubit, each edge a connection between them. So we have 156 qubits, yes, they're arranged in a certain way, and this is going to play a role on the type of operations we can perform on them. We have not seen transpiling, so the step where you compile your quantum algorithm in a way that fits the specific structure and the specific set of operations that a quantum system can perform. But as you can see, they have quite a peculiar structure, so this step is typically a bit challenging. There's a few edges and dots with different colors, and the colors represent how noisy they are, the error rate. Darker means better, and there are some things that are barely visible. So, for example, a connection here, it says no data available. That doesn't seem like a great start. And here, for example, we have another connection with an error that reads 1.0 10 to the minus 1. So, some qubits as well are bluish, with an error in the range of 10 to the minus 2, 10 to the minus 1. So this is one important problem we have with quantum systems, that is of noise. So if you run a computation, you will end up seeing results that you don't expect, because at some point in the computation, the state got damaged by decoherence, damaged by interference with the external environment, and so the result is not going to be correct anymore. I have a few bars to show this effect on a simple problem. Among the materials for the workshop, there's this one, the notebook that is called Qiskit Basic Example. What I'm doing here is I'm showing you the very first example with a particular entanglement state that is represented like this. It's a longer entanglement compared to the one with only 2 qubits I showed you earlier. It has 3, but the behavior is the same. We have either 0, 0, 0 or 1, 1, 1. So it's a correlation over of two states. This can be done with this simple quantum circuit. So a superposition and then a couple of 2-qubit interaction gates that create entanglement. Now, if you run, there's lots of implementation details I'm not going to go into because, well, the tutorial is quite easy to follow. But what is relevant is that we are using a simulator backend for the first example, which is called a staked vector. This means that we are calculating every single probability. So we are doing something we'd rather not do, but for the purpose of the simulation, we need this number. We run very simply the simulation. We wait for a bit, and then we get, here it is. And then we get our result. Our result is a vector which contains the amplitudes, the generalized probability that we need to account for, of observing the various states. Now, the states are ordered. So this one is the state 0, 0, 0. The next one is going to be 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. Like it's a binary progression. And as you can see, we only have a probability that is non-zero for the first one and for the last one. So these are our 2 extreme states, 0, 0, 0 and 1, 1, 1. It behaves as expected. There's a bunch of additional examples. If instead of calculating everything, we run a simulation which includes measuring, so we run a simulation where we add some of the stochastic, inherently stochastic nature of measurement, we create the circle in the same way. So we, again, create an object, we add some graphical elements to visualize it nicely, we add a measurement operation. Again, everything is quite simple to do. We just call the measure function and we say what we want to measure and where we want to put the result. And then we draw it and it looks like this. The first part of the circuit is the same as before. Then we have 3 measurement operations. The outcome of this is the following. Easier to read, 0, 0, 0, 1, 1, 1. The probability distribution is more or less 50-50, but not exactly. We have some stochastic measurement here. So there's 517, one of the two, and the other is 507. The more shots, the more repetitions of this operation you do, the more accurate is going to be your measurement. But well, you get the idea. This is what happens in an ideal scenario. So with no errors, with no noise, with no nothing. So we have already some approximation and we haven't even started to add a noise. What happens if we run this on a real quantum device? Well, we did that earlier when we had access still. And these are the results. So what happens is that you don't really need to do anything more complex than this. The only thing you need to change is the class that contains the backend. So you will need to create a different class with the runtime service. You will have access to a list of available quantum devices. Here we use a nice helper function which reads least busy. This system operates on queues, so as you can imagine, you may submit a job and then by the time it gets solved, well, you may need to wait a bit for the queue for your place in the queue. Still, we again recreate a bunch of classes that we need, a sampler object, and we do the transpilation because in a real quantum device we need to compile our circuit. We submit it. We wait for the results, and this is the result we got. So this is run on a real quantum device. Now, as you expected, we have peaks on the 2 states we want, 0, 0, 0, and 1, 1, 1. I'm running a lower number of shots because it's more expensive. 1,000 shots would be quite expensive. But then we also have states we did not expect. So once we observed 001, which should not exist, 010, and 011. These were created due to interference with the environment, due to decoherence effects. So even in a very simple system with only 3 quantum operations, we have a probability of reading the wrong result which is not negligible. Now, this is a rather small quantum device which was built in the 2022, I want to say. So the technology is at the pace it's been evolving. This technology is a bit obsolete, but still the probability of error is not negligible. Rather, it is a few percentage points, even in this very simple case. What happens if you make a longer algorithm, a more complex algorithm? So what I did here is I just created a very simple trivial example with a bunch of superposition operations followed by other superposition operations. Quantum computation is invertible, meaning that if I do a certain operation and then I repeat a certain operation, the result is the identity. So this should do nothing. This circuit should do absolutely nothing, with the exception of the negation of the first qubit. So the outcome of this should be 0, 1. Simulation, all is fine. Okay, this is all a simulation. Fantastic. Where it is? Aha. What if we run it on a real quantum system? Okay, we get our peak on 0, 1. Then we have 6 instances of 0, 0 and 1 instance of 0, 1, 1. Again, erroneous results. If we repeat this invertible operation a number of times, so we just make the circuit longer for the sake of it, the correct result occurs in fewer and fewer instances. So, for example, the circuit is twice as long. We have only 88 correct results. Some stochasticness. So now, if it's 40, if it's 3 blocks long, 90, and the error changes. If it's extremely long, so if you go on and on and on, we get the correct result only in 68% of cases. So, I mean, the technology is, when you ask me, do they work? Do quantum computers work? The answer is yes and no. Yes, in the sense that they work as expected. The physics is there. There's nothing surprising in their result, in their outcome. We can predict what is going to happen. And when they work, they do computations in the way they are supposed to do it. But, well, the engineering is still not there yet. So it is possible that in a few years, we will have small error-corrected quantum computers where this operation will be able to, we will be able to carry out these operations reliably. But it will take a few years before these can be used at an industrial level. So it may be nice to look at it for your use case, if you're a company maybe, to have someone that knows the technology and can know hype from solid science. But before you'll be able to solve your worldwide logistics on a quantum computer, well, let's meet up in RecSys 2035 or 40. Still, I will show you now a few examples of problems that can be formulated for quantum annealers, so you have a sense of what they can do, what are their limitations. But there is a great need to figure out what makes sense. So which types of problems make sense for quantum computers? Because you can stick everything into this. These are universal Turing machines. So everything that is computable on a classical system is computable on a quantum system. Some things are going to be much faster, some things are going to be much slower because the conversion doesn't make sense. And all the things you need to do, all the hoops you need to go through to convert a problem in a way that fits a quantum device, it's just going to be too expensive for the speed up you're going to get. So, and that is the great question. So what I can do with those in a way that makes sense. In this pack of slides, what I want to do is I'll give you an introduction on the QUBO formulation for optimization problems. We'll see a few problems that we might care about as recommender system researchers, so feature selection, clustering, community detection. And then I will spend a few words on the architecture of a quantum annealer. Now, why are we spending most of our time in the second part on the quantum annealers? Because one, it's the easiest to use in terms of the way you need to formulate a problem. Two, it's the largest one. Quantum annealers have in the range of 5,000 qubits, which is still small for a computational systems, but you can begin to experiment with problems that are small, but not trivial. So, first question, what do I need to do? The first step is you need to figure out what you want to solve. You need to formulate your optimization problem as a QUBO problem. We will see examples of how to do this and examples of why this may not make sense for specific types of problems. So this is already as a kind of an important distinction. There's going to be an important distinction between problems for which a QUBO formulation is reasonable and problems for which it doesn't make sense. So you're not going to be able to create a large language model with a QUBO formulation. Well, you can mathematically, but you're going to require so many variables and so many tricks that it's not going to make sense. Then, once you have your mathematical formulation, you need it to compile it so that it is amenable for the quantum annealer. And this step is called minor embedding. Fortunately, it's not something you need to do manually. There's heuristics that take care of the process. Then you run the annealing process. So what happens is that the actual coefficients, the values that you have put in your optimization problem, will be translated by the control electronics into magnetic fields that affect the interaction between the qubits. Paolo mentioned that quantum annealers work by evolving the energy of a quantum system. So what's going to happen is that slowly, very slowly, over the course of 20 microseconds or so, your magnetic fields will change ever so slightly so that the components of the problem you want to solve are introduced into the quantum system, which is then nudged towards the solution that you want. Again, this is something you don't have to control manually, but there's a few things you can do to control the process if you want. Then, after this very slow 20 microsecond execution, you can read the state of the system, so you measure the state of your qubits. That is the solution that the quantum annealer has found. Now, a quantum annealer is sampling from your energy distribution. So when you formulate a problem, you are creating a probability distribution of solutions, and your quantum annealer is trying to sample from those that work best. So there is a way to use the device to solve optimization problems where you want one solution. You just sample a number of them, and you pick the best one. But there's also a way to use quantum annealers to generate probabilities that are difficult to generate classically. A few interesting results, scientifically speaking, have been in this direction. So, for example, you can use them to do the Gibbs sampling. In place of the Gibbs sampling, if you want to train restricted Boltzmann machines. So there's a place for them in a number of applications. Once you have rerun your system a number of times, assuming you just want the best solution, you collect them, you have your energy, you pick the best one, and then you apply any post-processing you might want to apply, classically again. Oh, sorry, I will use classically occasionally to refer to traditional computing. This has become a physics habit.
Is there like an approximation how large of a problem you can solve? So, for example, if you have like an NP-complete like traveling salesman problem, how large can you actually go? Like 5,000 qubits.
There's a plot on that after in 3,000 slides. There's going to be a plot on that. So, QUBOs. Now, the acronym stands for Quadratic Unconstrained Binary Optimization. Quadratic because, well, it's in binary variables. Unconstrained meaning that it is not able to enforce hard constraints. So we will be able to constrain our problems, but through penalties, which means that at the end, we will not have the guarantee that the constraint has been met and that the solution is satisfiable, is feasible, sorry. oh, sorry, I flipped the quadratic. So it's the terms can be quadratic, and it can be used to represent all NP-complete optimization problems. So it is quite powerful, mathematically speaking. You can also use it to represent most NP-hard optimization problems because it is minimizing an energy. So there is a way you can fit most NP-hard problems there as well. This is the general formulation. So we rely on the notation here is n is the problem size, so the number of variables or problem we want to optimize. X is the vector of problem variables, so those we need to find, the binary ones. And Q is a square matrix of coefficients that will represent our loss function. So at this point, what we need to do is we need to figure out how to build Q. Usually the terms are decomposed into, we have the diagonal of Q represent linear terms, which would be, which would contain the coefficients, for example, telling us how much we want the selection of a certain variable versus how much we don't want the selection of a certain variable. And the quadratic term contains all the interactions between the variables, positive or negative. Advantages and disadvantages. Advantage is very simple. It's also very general. And if you are able to build an efficient QUBO solver, an efficient tool that is able to solve these problems very fast, then you can tackle a large number of problems. But there's a disadvantage, a few important disadvantages. One, you hide completely the structure of the problem you're trying to solve. You're just creating a bunch of coefficients. We will see that we hide constraints as well, which is the opposite of what one tries to do classically when you want to solve something very quickly. You try to leverage the structure of a problem as much as possible. So there is going to be always a disadvantage there. Second, even though the formulation is in principle very general, it's not a good fit for a number of problems. So there's a trade-off there. Again, nothing is a magical solution that will fit every type of task. Some solution, for example, if you worked on problems like the traveling salesman, well, these are highly constrained problems. You can formulate them as QUBO. You will find that it's extremely difficult to find a feasible solution there. So the annealer will struggle a lot. But then you may discover that other tasks like portfolio optimization or option pricing have simplified formulations to some extent that natively fit this mathematical formulation, which is kind of unexpected. So it does crop up in a number of places. Simple QUBO example. This will become useful in a few slides. So say that we want to find the value of two variables, a and b, such that a Boolean function, a not b, or a is different than b, is true. Quite easy. We have the truth table, a, b, and a different than b. How do we represent it as an energy minimization problem? Well, we need to create a function of a and b so that when the Boolean function is satisfied, the energy is minimized. So we flip it. Whenever the Boolean function is satisfied, our energy should be 0. Whenever it's not satisfied, the energy should be 1. How do we build such a function? Well, if a and b are 0, we want the energy to be 1. So we place a 1 there, a constant term. If either a or b is equal to 1, we want to push the energy down. So we subtract, and the function becomes 1 minus a minus b. If both of them are 1, what happens? Well, our energy would go far lower, would go to minus 1. So we need to be able to account for the fact that if both are equal to 1, our energy should go up again. we add a quadratic component. We sum a positive quadratic component, and that is going to push our energy up again. With this formulation and with this type of very simple tricks, you can represent any Boolean satisfiability problem as a QUBO. What if we have a binary function where A and B should be equal? Well, we can follow the same principle and we end up with again, we create our energy function. The energy is minimized when the Boolean function is satisfied. We go through the possible values, and we end up with this energy function, A plus B minus 2AB. So just as simple, we can reach this result following the same process. But it's unlikely we will need to use a QUBO problem and a quantum computer to solve this type of binary problems. So we need to add some complexity here. First, what if our problem is not quadratic? What if the problem has third, fourth, fifth order dependencies? What if we have nonlinearities? Well, to an extent, this is manageable because often when you have higher order problems, you can reformulate it in a way that makes them quadratic. For example, at the bottom here, we have a third order term, x1 times x2 times x3, and this can be transformed into a different type of term that only contains linear components. Depending on the energy of the two is not identical, so you may need to add other quadratic terms to shift it up and down. This depends really on what you need to do, but these type of conversions are possible. If you are unlucky though, these type of conversions will require you to add additional variables. So maybe you start with a problem that has 1,000 variables and you end up with a problem that has 5,000. So there are some trade-offs there. Complex question. Sometimes, yes, you can do sometimes you can do approximations to try to represent your problems in a different way or in a different space, but that really depends on what you want to do. And then if you do approximations, your solution is not going to be, it may not be optimal anymore. So there's a very large need, an extreme need, I would say, of figuring out what type of problems fit this type of formulations in a way that makes sense to use. Because you can do 1,000 different proof of concepts, 1,000 different small experiments, but figuring out what is promising in the long term is still a rather open question. What happens if the variables are not Boolean? Well, there's a few tricks you can use. For example, if you have a variable that is defined over a set of values, for example, here we have x defined over a set of 5 different values, we can use one-hot encoding. And so we end up with 5 different variables. One is associated to value A, the second to value B, C, D, E. We create these 5 variables, and then we have to add a constraint to make sure only one is selected. So doable, again, it costs variables. What if our variables are continuous valued, which is a rather frequent occurrence? Well, we can decompose them using binary expansion. We start with a real value and we decompose it as the summation over powers of 2, positive and negative, each multiplied by a binary term. It's like we are doing real value representation with bits. So we are creating a binary to real value map. And in the end, in our optimization our quantum annealer will select the powers of 2 that we want in order to represent that specific value. Again, we need variables, more variables. So we start with 1 real value term and we end up maybe with 10 binary variables. So it is doable if you have a mixed problem with most of the variables, in which most of the variables are binary, for example, and only few of them are real. If you have a fully real valued problem, this is going to be troublesome because it's going to be extremely expensive and the problem is going to be very large. So for the moment, I only gave you bad news. Skepticism is rather important. How to add constraints? Well, QUBO, as I said, the U stands for unconstrained. This just means that we have no way of guarantee that our solution will meet the constraints we care about, but we can add them in our loss function simply by adding a penalty. So we create a penalty function, which we will add to our loss function. The behavior of the penalty function will need to be the following. If our constraints are not met, we make the loss function worse by a certain amount. So if the constraints are not met, this penalty function should evaluate to 1, and in this way, this positive term will apply. So if the solution is not satisfiable, we add a term. This is something that you can, it's quite easy to do. The problem is that you don't have the guarantee of feasibility. So maybe your device, your quantum computer will be able to find solutions it believes are good, but they are not satisfiable because the penalty is too low, for example.
Is there a trade-off in the size of the penalty? Like if you make the penalty too large, can we have a problem that then the other look all too optimal, and it's harder to find?
Yeah, if the penalty is too small, you get unfeasible solutions. If the penalty is too high, you get solutions that are feasible but are not optimal. Fortunately, a rule of thumb is if you have an approximate order of magnitude of the energy of your solution, the penalty can have the same value. So if your solution has an energy of 50 and the penalty can be 50, this is typically enough to get a good trade-off. So it's not something you need to carefully fine-tune. Common penalty terms. Oh, well, typically you want, for example, to select only a subset of the values. You may want, because certain things are mutually exclusive, or you want to combine multiple things selected at the same time according to certain rules, or you want two things to be correlated in the sense that neither or either. Typical penalty terms are generally speaking Boolean functions. Do they look familiar? Possibly not. These are the very first two examples we saw. So even though they appeared simple and trivial, they are, but they do play a role in a number of scenarios where you want to constrain your problem. This I answered with your question. Penalty weight, you can use it with the same order of magnitude of your energy function. Now, there is a general way to take any problem. I'm going a bit quickly on this because, well, the mathematical details are a bit boring and I want to get to the more interesting part. There is a way to take any linear or quadratic optimization problem in binary variables and transform it into QUBO in a way that is in a closed form. So you just need to do a computation. You don't need to reformulate it. You see it at the bottom. And the constraints are added simply like these. With the constraints that are linear, like these, and C is your coefficient matrix. The penalty becomes the product of these two terms here, AX minus B transpose times AX minus B. So it's quite straightforward to do. The problem is that if you add lots and lots and lots of constraints, the cost function becomes very ugly. And so the annealer will struggle to find a solution. For this reason, warning, highly constrained problems, such as the traveling salesman problem, you will put the annealer in a situation where it will struggle a lot to find a solution. So I've seen a number of people that have tried to use this. If you are not familiar with it, in a traveling salesman problem, or even in a job shop scheduling problem, so where you need to allocate jobs to specific machines at specific times, you have lots of constraints in the ordering of things, in where a thing can be allocated, which job should be done on which machine, to which product, and so you have an enormous number of constraints. If you are in that situation, don't try it, it's not going to work. There are other ways where you can add constraints, but they're still experimental. There's a long list of known formulations of complex optimization problems, and NP-complete problems as QUBOs. You can find a couple of references here. They've been known for 10 years, so it's not, again, something challenging to do. But these are just examples. The thing we really care about are other types of problems, such as the ones I'm going to show you now in a moment. For example, feature selection. So why should we care about feature selection at a time when we can use more advanced methods to discover features for large non-structured data? Well, because we are not always in a situation of having that data. Sometimes these methods don't work well for us for a number of reasons. Sometimes we just want to keep the modeling simple, a number of scenarios. We want to improve scalability, we may want to improve interpretability, explainability, and so on. So there is a space for these methods still. The idea is that in a good feature selection, you take your problem, which has any number of features, and you want to identify a subset of them, which is going to, one, help you improve as much as possible the effectiveness or whatever solver or whatever, predictive model you're trained on them, and it should also reduce the size of the data so that the computation is faster. Now, we can write these type of problems as quadratic and constrained binary optimization problems, and the idea is that a binary variable will represent a feature. If the variable is 1, the feature is selected. If the variable is 0, it's not. We have two conflicting goals. We want the features to be as informative as possible on what we want to predict or classify, and we want to avoid redundancy, overlap, and so we want to avoid wasting resources on things, on information that we already know. A simple way we can approach this is that we can go back 20 years and optimize some information theoretical measure. So we can compute some form of correlation or some form of mutual information, for example, between the feature and the label, as well as between features. So we have an estimate of their redundancy and of their importance with respect to the label we want to predict. One possible example, again, these are very simple models. This is why I said we go back 20 years. The community is exploring ways to handle more complex ones, more effective ones. So there's lots of work to be done in this space. Mutual information is one of the various information theoretical measure that can be able to, you can use to measure the information that a certain variable has with respect to another. It's based on the Shannon entropy, so there's a whole theory there, which may be useful for certain scenarios. How can we create a feature selection algorithm based on mutual information? Well, if we look at the diagonal terms, so if we only take the diagonal terms, we want our feature to be as correlated as possible to the target label. So if we compute the mutual information between feature I and the target label, the higher the mutual information, the more we want the feature selected. Remember, this is a minimization problem, hence the minus there. But if we look at off-diagonal terms, we want to avoid redundancy. So we compute the mutual information between our feature and the target label conditioned on the second feature. So it's a quadratic term, so we are modeling the interaction between two features. And this tells us how much more information does a feature provide me given I have already selected another. So it gives us a kind of a second order effect. If the feature I provides little information, given we have already selected feature J, we don't want it. Both of these are negative, and mutual information is a strictly positive quantity, so every term in our QUBO function, QUBO matrix is going to be negative, which means that the optimal solution is going to select every feature, which does not seem very useful. So often, in these scenarios, what you need to do is you need to add a penalty, which is going to force your problem to select a specific number of features. It's a simple quadratic penalty. What happens is you add a term which is the summation over the actual values of your binary variable minus k. Essentially, you're counting how many you selected, and if the value is higher or lower than the target value, k, you add a penalty. This is just a very simple example of a constraint. the question in recommendation could be, what is our label? So in classification, we know the label. In recommendation, say we have items associated to certain features, descriptors of any kind. Simple example, we have movies, there's the cast. Or we have a hotel and we have features described in the hotel, the services it offers, location, and such. What is the label associated to a specific item? Well, the label relates to whether that would be a correct recommendation for a user. So we need to translate the problem in a way that would make sense for a recommendation task. There's a few approaches, you can do that, but I just wanted to describe one possible option. Incidentally, it's something we have worked on a bit in the past, just serves as an example of ways in which you can change the structure of the problem. So the idea would be, say that you have a content-based similarity model, an item-item similarity model, and you have a collaborative similarity model that works much better. Ideally, what you want to do is you want to select your features so that the content-based similarity is as close as possible to the collaborative one. You want to select your features so that you mimic as much as possible the behavior of the user. Why should you care for a content-based model if you already have a collaborative one? Well, maybe you need to deal with lots of new items. Maybe you want better interpretability. Maybe you want to be able to better control what things you are providing to the user. So maybe you want this type of abilities. So how could you approach this? Well, you take a good model based on a collaborative item-item similarity, SCF. You compute a content-based similarity based on a dot product using the features that you have. This is only serves as a way to get the structure of the similarities. And then you enumerate all the non-zero collaborative similarities. Why? Because these are the ones you want. And then you need to compute your label. So we compare the similarity values. In this simple table, so the columns are the content-based similarities, the rows are the collaborative similarities, and the two possible scenarios is in a particular couple of items has either 0 or greater than 0 similarity. So say that our content-based model has a similarity greater than 0 for a particular couple of items, but our collaborative model doesn't. What do we want to do? We want to remove that content-based similarity because the features that we have give us a similarity that, from the user perception, according to the collaborative model, should not exist. What if we have a positive content-based similarity and a positive collaborative similarity? Well, we like it. The two models agree. Maybe their value is going to be different, but the two models at least agree. And then you carry on. What if we have zeros in both models? The items are not similar from a content-based perspective, but are similar and are not similar from a collaborative perspective. We're fine. Again, the two models agree. Last scenario. What happens if we have no content-based similarity, but a collaborative similarity? There's nothing we can do. This is, unfortunately, a hopeless scenario. We have no features that will allow us to create a similarity. So that is a scenario we really don't want to be in, but it happens a lot. Now, we have identified a scenario in which we want to penalize the selection of features, and two, in which we want to encourage the selection of features. So this becomes a square matrix where we have two types of values. The things we want to keep are associated with -1, again, minimization problem. The things we want to remove are associated with +1. This is called, we call it the penalization matrix. This is an item-item similarity. We want to translate this into a feature-by-feature matrix because our binary variables are going to be associated to the features. And so, very simply, we compute a product between our item content matrix and the penalization matrix. And this is an example of a possible QUBO problem. So one variable per feature and a coefficient matrix that is simply the product of these comparison between the similarities. So you see, it's not complex to formulate a problem in this way. The question is whether the data supports this type of modeling. Now, does it work? Of course it does. It does to an extent, naturally, as everything does. There is a paper on it, so if you're curious, you can have a look. These are an example of the features that these type of models selects for a simple movie dataset. The movie's dataset is movie lens with a number of additional features gathered from TMDB with cast, crew, and such. You can see the features it selects. There's a number of collections, a few companies that tend to be focused on particular genres. So from a interpretation perspective, the features it selects make sense. What are the features it doesn't select? Oh, the data set includes movies that are very old. So 1898 is one of the old ones. Interesting thing, the Biograph Company. I bet no one has ever heard of the Biograph Company. It closed in 1916. So the type of features you select kind of makes sense. Now, feature selection is not the only thing we can do, we might care about. Another example could be clustering. Now, I'm going to jump directly to community detection. The idea of community detection is that you want to group the users. So we want to take users and try to identify whether they belong to a certain community according to a definition of community that may be as a matter of taste. So for example, you want to identify niches that focus on specific genres, on specific types of content, or that exhibit certain characteristics. It's a whole field. You can see it as a graph partitioning problem. So there's lots of algorithms you can do and you can use there. But the example I'm showing here is a very simple type of community detection based on modularity optimization. So what do we do? Well, our variable is the user. We have a binary variable for a user, and you want to decide where to put the user, in which community to put the user. Say we have 10 communities, we need to decide in which of them the user, to which of them the user belongs to. The formulation is, again, quite simple. We have two components. Q is our coefficient matrix. There's a coefficient that is 2 times the number of edges in your graph. This would be the number of interactions we have in our user item dataset. M is a matrix of coefficient, and delta is 1 if the two nodes belong to the same community. I'm using a graph terminology, if the two users belong to the same community. Now, M is computed based on the adjacency matrix of my user item graph minus P. P is a null model. I'm not going to the details of this, but there's a few formulations you can use depending on what type of graph you have, a bipartite graph or various types of derivative formulations. For example, the term can be the product of the degree of the two nodes normalized in a certain way. So again, it's quite simple to handle. So with these, you can create a very simple modularity minimization problem, and the solution of this problem will tell you to which community the user belongs to. Now, there is an issue, however, which is these. So if I have 100,000 users and 10 communities, I end up with 1 million binary variables. If I have 100 communities, well, 10 million variables. So this is not great as a formulation. Can we mitigate this? Yes. We may lose a bit of optimality, but for the purposes of trying to see whether this problem would make sense as formulated by QUBO and solved with a quantum annealer, what we can do is we can simply build an iterative approach where we have only 2 communities and we do binary splitting. We split the users in 2, and then we train a very simple model. In this example, there was a very simple non-personalized topopolar model. We train the model on the 2 communities. We see how it goes, and then we repeat. We pick one of the two, we split it into communities, we train the model, and again. So we have an exponentially increasing number of communities at every iteration. Oh, this I already went through. We split our community in two, we train a simple model. The example was just too popular, but you can do it, of course, with any model. The drawback is how much time does it take to train the model, considering that you have lots of different communities. We did experiments on, I think, 8 different data sets on a number of scenarios. So we tried to see how well it worked for a very simple, for a few data sets. And what happens is this. The line represents the NDCG at 10. The x-axis is the number of communities, the y-axis is the NDCG. So as the number of communities increases, the recommendation quality goes up. Again, this is a very simple example with a non-personalized model, so it has all sorts of limitations. But as you can see, in a few cases, we reach the top after a few iterations. In a few others, we never reach the best results. So at the bottom right, the site you like datasets carry on. If we look at what happens inside of the communities, we can see something like this. At the middle, in the middle, there's the result you get with the model trained on all users. Then we split in two. We have a community up here and a community down here. We split again in two, and the value represents whether the NDCG has increased or not. So for example, darker colors, red ones represent instances where the effectiveness improved, and blue ones where it didn't. So for example, there's a few instances where the effectiveness of the model went down. The communities probably became too small. But the number of them where it increased. So you have a way to decide which community you want, how large is the community that you want, according to what works best for that user. How do you select the communities? How do you split the communities? How long you train? Those are all things you can tweak and tune. So again, my goal here was not to say that this is a great model that you should deploy in your systems, but rather to give you an example of a type of tasks which would fit this particular type of formulation. And there's a number of them. I'll spend a few words on the actual architecture of the machine, so you have a sense of what's happening underneath. So much text. Now, in terms of solver, the quantum annealer is a meta-heuristic. So it's a solver that applies a certain type of, a certain process, a certain protocol to reach a solution. We usually call them quantum processing unit because they are analogous of the classical CPU of your device. And as Paolo mentioned, they worked by programming a physical system and then leveraging its tendency to evolve towards a state of minimal energy in a controlled way. The implementation of D-Wave is superconducting electronics. So you have a lattice of rings where the current flows in a certain direction. If the current flows, I don't remember which one, but clockwise, the state of the qubit is 0. If it flows anti-clockwise, the state of the qubit is 1. What about the superposition? Well, it flows in both directions at the same time. This is achieved with certain types of insulation, so it's a nice technology to look at. How do you apply coefficients in practice? Well, the coefficients become magnetic fields. Once you submit your problem and you have that the quadratic term between two variables has a certain value at 0.3, that value is going to be translated in the intensity of a magnetic field, which is then slightly tweaked and tuned as the evolution of the system progresses in order for the system to reach the final configuration. So there's a direct connection between the coefficient you calculate and the actual physical system that is running the computation. Whenever you have a linear term, so a weight associated to a specific variable, that becomes a magnetic field that pushes the rotation of the current in a specific direction. Whenever you have a quadratic term, so a coefficient that connects two variables, that becomes a magnetic field that connects neighboring qubits and that allows them to interact with each other. Fortunately, you don't have to manually control this process. Still, the coefficient you put is the magnetic field you get. To go back to a question I was asked earlier, the connectivity of the problem poses some challenges. So in the example I showed you earlier, the feature selection one and the community detection one, we always had a dense problem, meaning all variables had a quadratic component. But there's no such thing in practice as a fully connect quantum hardware because the architecture is planar, and so there's a limit to how many neighboring qubits you can be connected with. The quantum annealer has a specific topology, certain arrangements of the qubits, so you need a compilation phase to go from the abstract formulation to the actual hardware. This is an example of a topology of a quantum computer. Again, the dots represent the qubits and the edges the connections between them. This is a rather old topology. It's still around, but here every qubit is connected to other 6 ones. So a machine that is built with this topology, even though it may have 2,000 qubits, each of them is only connected with 6. So it's extremely sparsely connected. What happens is that you may not be able to fit all the connections that you need. There's a number of topologies. This is another. It's a more recent one. You have 20 connections. I believe this is the current state of the art. So still, the quantum computer has 5,000 qubits. Each of them is only connected with 20. So how do you fit them? This process, which is again analogous to the compilation of any program you can write classically, is called minor embedding. The unfortunate bit is that it's more difficult because it is a graph mapping problem. So let's say we are in this situation. We have a problem graph with 3 variables, A, B, and C, coming from whatever problem we have formulated. Again, toy example. And we want to solve this problem on a QPU which has a square architecture. So we have 4 qubits connected in a square. They don't fit. So how do we fix the problem? Well, the trick is we replicate variables. So we use, for example, we place our variable A, associating it to 2 different physical qubits. The 2 qubits will represent the same logical variable, but will be 2 different physical entities. Now it is going to be possible to connect A to both B and C, but at the cost of a qubit. Here we are not copying a value. What we are going to do is we are going to create a correlation between 2 qubits. Each of them will evolve independently, but the optimization problem will be written in such a way that their value is going to be strongly correlated. So at the end of the execution, they will have the same value, or they should have the same value. So we are not copying the value, rather we are kind of pushing them to have the same value. This is just to give you the response, the answer to this question, actually. So an example of a 3-variable QUBO problem that would have this type of triangular shape is this. We have quadratic components to all couples of variables. In terms of formulation, what happens is we create a new equivalent QUBO problem. So what do we do? The first term is the interaction between 1 and 2. We have split our variable 1 in 2 different qubits. x2 is only connected to xa, so we need to change that. The term is going to be xa, x2. This is going to be done automatically, so you don't have to take care of it, but it has an implication on the number of qubits you need to use. The second term is the interaction between variable 1 and 3. 1 again was splitted, so variable 3 is only connected with variable b. So, okay, we need to change that as well. Bam. Second term, xb, x3. Third term, x2, x3. They are directly connected. No problem. We copy the term. Now, we want xa and xb to have the same value. So we need to add a constraint or a penalty. An equality constraint. This is I think, the first example we saw at the beginning of this slide. So they do play a role. Now, if your problem is highly connected, what is going to happen is that you will need to do lots of these. You will have to replicate your variables lots and lots of times. So you're going to waste qubits. So the higher is the connectivity of your problem, the more qubits you're going to need to represent it, and so the larger the machine you will need. So this is going to constrain the feasibility of your problem. It represents the number of qubits, the number of variables, and the number of qubits that you need according to a specific topology. Chimera is the first one we saw. Each qubit is connected to only 6 other ones. Pegasus is in the middle, I think it's 15, and Zephyr is the most modern one in which each qubit is connected to 20 of them. So if you look at the numbers, you can see that, for example, for 100 variables, you already need 1200 qubits. This is a fully connected problem. So there's a factor of 10 between the number of variables of your problem and the number of qubits that you need for a fully connected one. Even though there's a difference, the difference is, well, is visible, so technological improvements are doing wonders. Still, this is going to be a problem you need to take into account. To conclude this block here, I want to leave you with a few open research questions. So if you are interested in this type of technology, what is that needs doing? One, new formulations. So to see whether there's something that can fit this particular formulation, that has the right properties or the right structure, considering the limitations of the device in terms of connectivity, in terms of the time it takes to create the QUBO formulation. It's easy to show quantum advantage if you ignore all the cost of creating the formulation and all the cost of post-processing. So the difficult bit is being able to see whether there is something that makes sense considering the whole process. Developing way to take known formulation and compress them to reduce the number of variables, to develop better ways of encoding their terms, their constraints. And if you want to go a bit beyond the information retrieval and recommendation system field and work with a more general perspective, there's a great need to develop new minor embedding algorithms, so graph mapping problems. There's a few approaches one can leverage. We've been doing some research in this direction as well. There's a growing field of AI for quantum that tries to solve these problems. So you're not using quantum computing to accelerate artificial intelligence. You're doing the opposite, trying to mitigate some of their limitations, and there's a lot to mitigate. And develop ways in which you can split large problems into sub-problems. So what happens if you have a big problem that doesn't fit this architecture? Well, you need to split it. How? Operations research the operations research field has developed a number of methods, but they are not necessarily going to fit well for the particular characteristics of your problem. So how do you split it in a way that makes sense considering your domain? So in a similar way, in which you develop a new architecture for a machine learning model, here you can develop a new QUBO problem, a new cost function. If you want to go to the next level, there is a lot of need to work with gate model, so universal quantum computation. There has been a few years ago a paper that claimed super polynomial speedup for a quantum version of a recommendation system. That claim was later debunked, I should say, by Yuintang, showing that this claim was only due to the particular encoding of the data access method, and it was possible to do that efficiently, so one didn't need a quantum computer. So the discussion is still ongoing. Be skeptical whenever someone tells you that they've proven quantum advantage. The answer is likely that it is going to be possible only for extremely specific or extremely constrained type of problems, so it may not be as relevant as it might appear. Before I show you a couple of other examples, I want you to pause for a moment in case you have questions. I went a bit fast on a number of things, but I hope the material, if you're curious, will be sufficient. If you have any questions after this tutorial, please drop us an email. We'd be happy to chat.